Good afternoon, I'm Joel Carpenter from the University of Cambridge, and today I'm going to be presenting holographic mode group division multiplexing. So that is utilizing computer-controlled holograms to both excite and detect specific modes of a multimode fiber, with a view to sending independent channels on separate fiber modes. So I'm going to start off with a brief overview of modal propagation in a multimode fiber. Here we have a multimode fiber, and at some wavelength it will support some number of modes, maybe 20 modes at 1550. And the number of modes the fiber supports will depend on things like its geometry, its refractive index profile, and of course the wavelength that you're using. And all of those parameters will also define the speed at which each of the modes propagate. And the fact that each mode doesn't travel at the same speed is a problem. It's a problem called modal dispersion. And it means if you send a sharp pulse of information from one end with the power distributed amongst many modes, then you'll get your information arriving at the receiver, propagated by many different modes, which each arrive at slightly different times, and causes a smearing of your input waveform and a closing of your eye diagram. Now, just because your fiber supports some wide array of modes doesn't mean you have to use them all to propagate your information. And there are a lot of different techniques around for selectively exciting small numbers of modes. But the most flexible is to use a liquid crystal-based computer-controlled hologram to control the way light is coupled into the fiber, hopefully excite some advantageous group of modes, which all travel at very similar speeds and undergo minimal modal coupling. So one such system looks like this. You start with a simple Gaussian laser source modulated with your channel of information. Its beam is incident on your liquid crystal-based spatial light modulator, your SLM. This is your hologram, which consists of an array of pixels, with each pixel capable of independently altering the phase of the incident beam. And that new wavefront that it creates is then Fourier transformed, sometimes resized, and then coupled into the multimode fiber. And with any luck, your information should now arrive at the receiver, propagated by very few modes, which all arrive very close together. So this causes our eye diagram to open up, which means we can now send information over longer distances at higher data rates or both. And this kind of technique has been demonstrated by my own group at Cambridge, as well as the guys at the Institute of Telecoms at Warsaw Uni of Technology, and some good work by the optical comms group at Stanford as well. This is the first part of any modal multiplexing system. You need the ability to get the modes into the fiber that you want, and it has the desirable consequence that because it's modally selective by its nature, you're also combating modal dispersion at the same time. But it should also be possible to take this idea further, to truly exploit the modal nature of the fiber itself. So what if, rather than having a single laser modulated with a single channel of data, what if you have multiple lasers modulated with multiple independent channels of data? That each of those beams is incident on its own hologram, its own spatial light modulator, which assigns each beam, each channel, its own unique spatial distribution, which is then Fourier transformed, possibly resized, and then coupled into the same multimode fiber. Now, if you've chosen those input distributions correctly, they should still be diverse enough at the output end that an additional hologram or holograms can distinguish between them and split them back into their respective data streams. So in this way, you've turned the modal nature of the fiber from this unwanted cause of dispersion and distortion to a degree of freedom, which you can now exploit to increase the bandwidth. So moving on to some actual experimental results. So if you want to be able to adaptively excite specific modes in your fiber using your SLM, probably the easiest way to do that is to treat it just as a adjustable diffractive grating. That's a grating with an adjustable period or adjustable phase tilt, which causes a spot or pair of spots to steer across the core of the fiber. And that's what we're looking at here. So the small spot on the left relative to the 50 micron core produces the experimentally observed near field leaving the fiber after 2 kilometers on the right. And you can see that even though the lights travel quite some distance, it's still dominated by the launch conditions. That is, central launch gives rise to lower order modes, very compact. Large offsets near the core cladding interface give rise to higher order modes, which take up the entire cross-section of the fiber. Getting a bit fancier, it's also possible to calculate more sophisticated holograms with specific fiber modes in mind, and that's what we've got here. So on the left, holograms have been calculated for each of the roughly 120 modes of the fiber, which produce the experimentally observed far field on the right. So this is just a real-time video of me scrolling through a drop-down box on my computer, which allows me to selectively excite whichever mode I'm interested in. Now I've turned up the attenuation of the modes quite a bit here because I wanted to show a few different features. First, you'll see that the background noise is not evenly distributed. There's an area roughly the size of the multimode core in which noise is suppressed and a very high quality mode is placed in the center. You'll also see that in this case I've offset my modes from the center of the far field so as to avoid that spot of undiffracted light at the center. It's also possible to center your modes so as not to pay the 3 dB penalty of duplication. Alternatively, if you've got more than 2 phase levels on your spatial light modulator, you can also steer the mode away from the center without having to duplicate it. Putting that into practice, what I've done here is I've got a 1300 nanometer single mode fiber, solved the modes for it at 660 nanometers, which gives you 4 modes, calculate holograms for each of them, and then launch them. And you can see that because it's only a few mode fiber, and because it's only a very short length, theoretical and measured results match up pretty much perfectly. So mode in equals mode out. You can even change the orientation of the mode if you so wish. A less trivial example is to do the same thing for a truly multi-mode fiber, that same 2 kilometer length of fiber from before. So what I'm doing here is trying to launch each of the 120 modes at 2 different orientations. And you can see that whilst the cross-sectional area of propagation is consistent between the launch and the measured result, you can't identify the individual modes like you could for the previous 4-mode fiber. And this is because of modal coupling. Modes will tend to couple most strongly with other modes in their own mode group, which from a dispersion point of view is not a problem because modes within a mode group travel at almost identical speeds. But it does mean that you won't be able to identify the individual modes just by looking at them, because they're going to have very complicated phase relationships between them. With the exception of the lowest order modes. So the LP01, the Gaussian, the LP11, the 2-lobe bow tie looking thing. You can see that even though the light has traveled 2 kilometers and has had 120 modes to choose from, it's pretty much stuck with the mode it was launched as. So the Gaussian goes in, looks like a Gaussian on the way out. The LP11 still has a null in the center of the fiber even after 2 kilometers. And if you put a polarizer there, the LP11 is even more obvious. And that's all about getting the modes that you want into the fiber. The next bit is trying to get them back out. And to do that, you need some sort of optical pattern recognition system. The simplest of which is to just do a phase-only autocorrelation. So if you wanted to take the LP11, which has an intensity and phase profile like this, you simply take the phase profile, the conjugate phase. You can add a grading structure over the top or a phase tilt if you want to move the correlation peak away from the center, and you use that as your filter. So you can see that for a 2-mode fiber, when the Gaussian is present, you get a diffuse structure. When the LP11 is present at the correct orientation, you get 2 strong correlation peaks. So I've done a very crude experimental realization of this. I've gotten a 2-mode fiber. I've changed which modes are excited at one end by changing the offset of the launch. At the other end, I've got my LP11 correlation filter. You can see that when the LP11 is present, you get 2 strong correlation peaks, and when it's not, you don't. You get more diffuse patterns. It's also possible to calculate more complicated, more sophisticated pattern recognition holograms. So this one, for instance, has been calculated to accept one mode and reject all other modes of the fiber. It's kind of interesting from a theoretical point of view, but in reality, you're going to get such a mess of a complex distribution at the other end for any appreciable length of fiber, as you saw in the other examples. It's unlikely you're going to be able to get away with calculating something straight from theory and plugging it straight in. What we think we're going to have to end up doing is taking a more adaptive approach. You have some input to the fiber, which produces some output distribution, and you take advantage of the fact that you can adaptively change the pixels on your hologram to adapt to that output distribution and form your correlation peak. However, it might not necessarily be required to get as complicated as that, because most other groups who have done modal multiplexing have gotten the modal diversity they need at the output end, simply using single mode fibers offset along different positions on the multimode core, or the same thing with photodetectors at different positions along the multimode core, or even stuff like mirrors with holes drilled through them, directing light to two different detectors. And all of those also have holographic implementations, using fairly simple holograms. With the added benefit, of course, then, that you can change them and adapt them without moving parts.